Thanks for the introduction. So I'm at the Utah Avalanche Center. Started kind of briefly in February, and we've been building out over the last few years an operational dashboard, which combines some of the tools that come from Switzerland, as well as some of the data that we're working on and collecting in Utah. So we'll just be kind of talking about that. And I feel like this pairs really well with the last section because we're using a lot of data that's coming from SNOWTEL and a lot of crossover there. So before we started, we really wanted to identify the key goals in building an operational dashboard. And by having these North Stars, we're going to be able to kind of make sure that we're staying true to our metrics. And so when we went out and started building this, we wanted to increase the accuracy of our avalanche forecasts. We wanted to create staff efficiencies. So we wanted to make sure that, it's 4 a.m., I have to look at so many different tabs. How do I reduce the number of websites I have to look at to get the information that I need to make that forecast and present it to the public? We wanted to create visualizations. Several years ago, I got to go to NREL, which is a national lab, talk to the visualization people there. They said, I spend 2 weeks building visualization. Scientist comes in, looks at it in 3 seconds, gets what they need, and walks out. Like, that's our goal, is to make sure that we build something that forecasters and ski patrol can pick out that relevant information really, really fast. And then that's how we know we did our job. And then lastly, we want to be able to kind of catch nuanced trends and instabilities that could be happening within the snowpack itself. So in particular, like the use case that comes up more recently than not is like radiation recrystallization in Upper Little Cottonwood Canyon. And so we kind of use that as a test bed to capture those nuanced instabilities. So to give like a high-level overview of how the project is working from a workstream perspective, I'm just going to kind of highlight how that works. And so we start with data. And so right now there's 2 schools of thought kind of within the Swiss operating forecasting using SNOWPACK. You can drive the model itself with weather model data, gridded numerical weather prediction model data, or you could drive it with weather station data. And so we elected to kind of go with the weather station approach. And so with this, we're going to be capturing all the surface energy balance variables that we just learned about in the previous talk to drive the model. To get items out into the future so that we can get a look into how the snowpack is going to be reacting to those forces, we're going to couple that with numerical weather prediction models. So that's your, open up your iPhone, get that weather forecast. So that's what we're going to drive to look at the forecast information into the future. We're also going to start focusing on collecting data for validation and optimization. And so this is, snow pit data that we're collecting from various sites that we've identified as relevant and important. And then we're going to use that information to help improve the skill of the numerical model itself. And then we're also interested in collecting data from new and advanced technology. So I'm not sure if folks in here have heard of like the GeoPrevant radar detection systems. They're pretty popular in Europe, but they can detect the difference between a skier triggered avalanche and a natural avalanche, and they can measure the speed of the avalanche and the size of the crown. Other systems that we have access to are like the infrasound detection systems, which use microphones within avalanche paths. The baseline, or kind of the meat and potatoes of the program, is the SNOWPACK model itself. So this comes from the SLF. They developed it in the early 2000s, Michi Lenning and others. And this is a physics-based model, so it's solving the conservation equations for mass, momentum, for water and heat vapor transfer. It's going to provide us information on snow stratigraphy primarily, and it's going to do it at really, really high temporal resolution, right? So we're getting really fast and better understandings of snowpack structure. However, obviously, we're sacrificing some accuracy by doing so. The model itself was developed and used and is used in an operational setting in Europe, Canada, and it's starting to migrate over to North America as well. And then lastly, over the last few years, more recently, there's been some advancements in using machine learning to develop instability models, which depend on a lot of the instability parameters that we've been talking about earlier today. And when we couple a snowpack with weather information and these instability models, then we can get detailed snow stability profiles. We can highlight some of these subtleties, like we talked about, like an RR event or near surface faceting event, as well as persistent weak layers. And that's Stephanie Meyer and others. The other model that we're also driving, or using SNOWPACK to drive, in addition to weather station data, is the danger level model. So this would be a danger level forecast that's provided in addition to the other items that we talked about. So these stations don't look as cool as the last talk, but we've been going through and outfitting weather stations across the different forecasting regions in Utah. And so we've been doing this for the last 2 years. And so in order to drive SNOWPACK, we need key information such as net radiation, which we talked about. If we're not using net radiation, we can couple that and supplement with snow surface temperature itself. We're getting the other auxiliary variables such as relative humidity, temperature, and whatnot. And we're partnering with other folks such as SNOWTEL to kind of expand our network in that region. In order to kind of combine what we're talking about with validation and optimization, we were just talking about, improving runoff. We're also very interested in deploying snow temperature thermocouples. The model itself is predicting that internal energy of the snowpack, and when we have that information, that temperature information, then we can go back through and re-optimize the model. So we can validate and then optimize with that information. Because we have such a dense network of stations, we needed to kind of identify like what was going to be our gold standard and where can we do other validation and testing. And so the Atwater study site has a lot of stakeholders. The Department of Transportation is interested. The University of Utah is also very interested, has a lot of research going on at that site. So we've been riding the coattails of other organizations and adding instrumentation, even including the Luft WS100 we've been evaluating as well more recently. So we just mentioned a little bit about validation and optimization. And so for these different parts of the project, to build out a robust validation and verification strategy, you need to make sure that you're, making sure that the numerical model under the hood is providing the information that you think that it's providing. So, my code says 2 + 2 = 4, not 4.1. I make a change. Is it still 4? I want to make sure that I'm always getting the same answer. So we're building out unit test cases. We're also collecting, as I mentioned, this validation data. So we're creating standard procedures for collecting our pit data at our specific test sites across different regions. So that way we can use that information, gets uploaded to SNOWPILOT, and then run those validation tests to score the model over time. We're also kind of starting to look at new tools. So you may have heard of like the Propagation Lab SnowScope. It's a small startup. It's the newer version of one of the older snow penetrometers that was developed a few years ago. So we're starting to work with that team to collect snow profile information. And the benefit of that is instead of having to dig a 3-meter pit, you can go ahead and just probe really quickly, get that validation data, and then compare it against your model output. And then, as I mentioned, we're doing the snow energy validation with snow thermocouple arrays. So there was some work that was done on the SNOWPACK anisotropy a few years ago, and that kind of optimization technique was developed in there. On the instability side, the Utah Avalanche Center is really lucky. We have a ton of people who ski in the Central Wasatch, and they're really excited to report avalanches. And so we're collecting that information, putting into a standardized database, kind of trying, again, to make sure we structure our data in such a way that it's being formatted that we can use it for validation. The GeoProvant system is pointed at near the Superior Slide Path in Little Cottonwood Canyon. So we're getting really high fidelity new snow avalanche information. The infrasound, and then we also have a roadmap to start using satellite data as another validation source. Danger level is a challenging subject. There's a lot of bias, human bias in danger level, forecasted, as well as if you went back to hindcast. So one of the methods that we're exploring is using avalanche observation data as well to kind of do a multivariate mapping between the different metrics. So avalanche activity, danger level, and snowpack structure. This is just a quick little printout. Comes from an open source tool that was developed between Simon Horton and Florian and others to score the SNOWPACK model. And so we can score based on weak layers, or lemons was the popular term that came out of that work, crusts, precipitation particles, or total bulk similarity. And this is just a sample. We were changing the boundary layer conditions within the model, and so we were able to improve it for a particular point in time. So now that I've provided some background, I'm just going to give you a quick snippet of the operational dashboard. So this is intended to be a really high overview of that dashboard. And if you have any technical questions, I'd be happy to kind of divulge more into that. When we approach the dashboard, again, getting back to these fundamentals, we really wanted to address some really key questions. And the first visualization that we decided to present our forecasters was an instability timeline. And the goal of this was to answer those questions, right? It's 4 in the morning. How stable is my snowpack? If an avalanche was going to happen, how big would that avalanche be? And if an avalanche is going to step down to another weak layer, how big would that subsequent avalanche be? So this is a screenshot from last month. And so on the x-axis, we're going from the past. Our red dashed line represents our current time. And this is for one particular site in Upper Little Cottonwood Canyon. And then we're going out into the future 48 hours so that we can get an understanding of how are those instabilities changing over time with either new load or no new load in this case. On the y-axis, we have a measure of instability. So it's basically a probability density function. So it goes from 0 to 1, with 1 being very unstable, 0 being bomber and ready to go. We elected to depict 3 layers of concern. And so you can see at the time in this presentation, or the time the screenshot was taken on March 6th, we had 3 layers of concern and 1 layer that was persisting over time. If we take a deeper dive, we supply also the depths of those instabilities. And so we can see that those layers 2 and 3 themselves are actually really deep within the snowpack and actually are a result of our persistent weak layer that was long lasting throughout the season. And our surface, our layer 1, our most unstable layer, was at 72 centimeters and was near the surface and problematic, which we'll show later. So this is going to answer, right, how deep are those instabilities in my snowpack and those particular layers of concern. The second profile, or the second visualization that we highlighted is a profile. It's like, okay, so now I have this instability, right? I have something that I know is problematic, but where in the snowpack are those weak layers and what kind of instability do I have? And so we elected to present snow profiles. So if you've seen talks on snowpack, these probably look very familiar to you. And if you haven't, this is just like you would dig a snow pit. It's a profile in time with the x-axis being the hand hardness, y-axis being the snow depth, and then that top x-axis being that instability metric that we were showing on the other slide. But now we're getting it for every single layer within the snowpack. And again, we can see that that weak layer is a near surface facet crust close to the surface. On the right-hand side, we have the same plot, but it has a date picker, so it allows the user to go back in time and compare those layers and how they changed over time. So you can see, on the third, before we had that overburden stress, that layer wasn't really problematic and the instability wasn't really relevant. Throw some new snow on top and all of a sudden we have the potential for avalanche. And the third display that I wanted to highlight is the danger level timeline. And so we really wanted to highlight, how has the model danger level changed over time? Is it increasing, decreasing? And then the other aspect that we hope to use this tool for is understanding over forecasting events and how that danger level has changed. I have persistent weak layer. I've been forecasting 5 days in a row, considerable danger. Is it time to drop it back to moderate, or do I still keep it at considerable and keep crying or potentially crying wolf? So again, this is for a single elevation band where the station is run. In the center, we have, or on the bottom here, we have a legend helping depict that. So in the center field is the flat field simulation, which is representative of the weather station. And that's where the simulation is run. In SNOWPACK, we can run what's called virtual slopes. So we're adjusting the precipitation, the wind speeds, and the radiation energy balance into the snowpack to get north, south, east, and west, those cardinal aspects. And these pie charts above represent that modeled danger level, with yellow being moderate and orange considerable. And so you can see here that we are able to kind of highlight over the past 5 days, how has my danger level evolved, and then in the next 4 to 8 hours, how is that danger level changing, and should I keep it the same or should I drop it? So it's just intended to provide this secondary gut check to the forecaster, like, yes, I need to rise the danger, yes, I'm ready to lower it. So I wanted to highlight some case studies. I'm a statistics guy, so I love big numbers, but we just haven't been running long enough to really correlate these to big numbers yet. And so just going to highlight the March 8th event. So I was showing all those near surface facets around that melt freeze crust, and just wanted to highlight that we had quite a bit of activity with this really impressive result. Just down canyon that was submitted by a pro observer, which failed on that near surface faceting. The other event, which came from last season, we've had a radiation recrystallization event earlier this winter as well, but this one was pretty well documented. We had several reports and catch and carries. And again, we were able to catch that near surface facet. It's really hard to see, but there's this little faint section of blue which correlates to what the model would call facets or depth hoar. And on the right-hand side, we have that snow pilot profile, which highlights that near surface facet. Our forecaster, who lives up canyon, went out and inspected that reported avalanche, got ECTN 14 times 2 and a CT7 on that buried radiation recrystallization crust, and was quoted that there was a slight mill freeze crust with small grains, broken stellars with sharp edges above the crust, below the surface in this location, and other areas that mill freeze crust with facets was closer to about a foot. So we had really nice case study here for the radiation recrystallization. So to just kind of recap, I just want to highlight that we've been starting to establish data collection in other regions this past season. We're really focusing on getting that model chain going and getting that proof of concept running, building that dashboard, getting input from forecasters. We elected to build the system. Instead of, I was running it on a machine at the University of Utah, which wasn't cutting it because it was crashing every other day. But now we're running on Microsoft Azure, and we're using a Power BI basically dashboard. And that allows us to iterate. We've probably gone through over 100 versions of this dashboard in under a month with the developers. And so it's just a really rapid turnaround to get that feedback, which I think is really important. And then we're continuing to develop our validation data collection strategies and kind of write those standards so that we can really start collecting that data. This summer, we're going to be working on exploring new new weather modeling tools. Right now, we're running the HER. So I get the joy of working really close with Jim Steenberg, which is awesome. And they've given us some other opportunities to work with other tools such as the HREF or the GFS, some other tools that maybe different regions would like to have over the HER. We're also interested in doing some downscaling to the particular points of those locations so we have better forecasting tools. We want to operationalize that optimization strategy that we were talking about. So we have one station with that temperature thermocouple array. We're looking to expand that to 3 or 4 more stations this winter, and then improve that weather station pipeline, right? Weather station, while they're super robust, sometimes you either lose data, a sensor goes down, and you need to figure out what am I going to do with that missing data so that I can fill that gap, get the model running, and get that data to the forecaster at 4 a.m., right? We can't have any shutdowns. So I know that was super high level, but feel free to reach out with any technical questions. Implementing this operational strategy has been a really big task, but we're learning quite a bit as we go along. And lastly, I just want to thank my colleagues too at the University of Utah, at the Utah Avalanche Center for all their support. And I do want to thank my colleagues at the University of Utah, Eric Pardiak, and that Snow Research Lab. And then we've also been working with Dr. Betty Richter at the SLF. And having someone, who's 2 doors down from Nander, who helped write the code, knock on the door, ask the questions, has been really helpful. So learned a lot, trying to institutionalize it. So thanks.
How often did you thin layers?
Yeah, so the SNOWSCOPE probe we've been testing this winter. And so we've worked with the propagation labs to get some probes to all of our different regions. We've had some forecasters that love it. We have some forecasters that are still on the fence about it. So
A lot of side by side.
yeah, and some of the developers too have been working on that. And they're Salt Lake guys, so if anyone's interested in talking with them directly, I'd be happy to connect you guys.
What do the forecasters in the Utah Avalanche Center think of all of this in general, integrating this kind of AI type thing into forecasting? What's the general feeling about it?
I think they're mostly excited. Obviously, there's hesitation, but they've been really receptive, and they've been providing feedback, critical feedback, which to me is good because that means they're looking at it, they're starting to ingest that information, they're trying to make it better so that they can actually use it. So we're going to be really ramping up this summer to make sure that it's more robust, so next year that they can actually use it in that morning forecast.
I guess I missed how it would help you not over forecast because weather station data is all in the past.
Yeah.
SNOWPACK data, and sometimes what's affecting your stability is the future.
Mm-hmm.
So how would it inform whether or not you're going to over forecast or hold danger when that's dependent on future circumstance, I guess?
Yeah. So right now, in order to get future forecasts, we're coupling with numerical weather prediction model data. And so we can forecast up to about 48 hours into the future. And obviously, that's only as good as your forecast. So, if the HRRR bombs the precip, then, it's not going to do a good job. So obviously, it's as good as that weather model. But looking to bring in, so the HREF is the high resolution ensemble forecast. And so they're getting 12 to 13 members, which can kind of help hedge some of those variabilities that you see in different forecasts. The HRRR is just a single member forecast. So.
What's the ultimate scale you want for the models? You want us to keep it within Utah, or are you hopefully eventually looking to expand into other states and different forecast centers as well?
Yeah, so we've been working on making sure that this pipeline is repeatable. And so, yeah, we're definitely interested in expanding to other areas right now. And when it comes to, so I'm a Mesonet guy, so I love weather stations. So just getting started, right, is the biggest question. What instruments do I need? How do I run those data logger codes? And so we're also willing to help, make sure that you start collecting that data. That's the first step. So, but the SNOWTEL network upgrades would be ideal, right? So that's one of the reasons we picked Atwater is because it is at least I was told it was a SNOWTEL supersite. I'm not sure it is anymore. I thought it was, but we definitely have at least all the instrumentation there to run it. So.
I was wondering how you decided to run it with the station data versus the numerical weather models, just because sometimes I've seen the numerical weather models run stuff at a better accuracy than the weather station model and vice versa.
Yeah, so my understanding, there's a paper from Morrison et al. 2020, and there's a lot of folks on there, right, and kind of talked about adoption and whatnot. And to me, the biggest hurdle to adoption in the United States has been trust and accuracy. And I felt that using weather station data and really validating the system at points would be a better approach for that than using gridded data, trying to do kind of this simulation approach that you see in other areas. You're running with numerical weather prediction data, it's got a lot of advantages. You can get, as many profiles as you want for a particular location, but that's also expensive. So, yeah.
Is your current modeling workflow reincorporating in validation kits that you're digging right there as you work through the winter, or not at this point in time?
It's not operational, yeah, but yeah, we're working on that.
Last question.
Sorry.
What's the density, I guess, of weather stations per elevation band that you would need for confidence in this
height scale?
Yeah, that's a great question. I mean, so right now we're trying to do one per region. I don't know a good way to kind of depict how big a region is, but a couple drainages, I would say, and spatial heterogeneity is a big question and problem with any kind of measurement or modeling in the mountains, as we all know. So, trying to think of strategies. Francis, I can't remember his last name, but Francis, he's a postdoc for Simon Fraser, and he did this really cool analysis of using this data to kind of do slope scale instability forecasting, which would be hyper-localized. But yeah, how do you go from slope scale to kind of regional scale? I think it's an open problem. Thanks.
That was awesome.
Thanks.